Welcome PCS members and friends to our PCS IBS seminar. Today we have a pleasure of hosting Mr. Pablo Bermejo from Donostia International Physics Center in Spain. And our scientific host today is Dario, who will introduce our speaker. Welcome, PCS.
Okay, yeah, thanks, Dylan. So it's a great pleasure to have Pablo today with us, who is speaking from this beautiful place, as we can see in the first slide. So Pablo is a PhD student currently in Donostia International Physics Center, and his supervisor is Roman Orus, that for people who don't know is one of the leading class experts in tensor networks and more generally in building smart ansatses in order to find many-body quantum states in general. So Pablo was, did a double master degree, apparently, one in Paris-Saclay and the other in École Normale Supérieure. And then he became a PhD student in Donostia, but at the same time, he's also working as a senior scientist at Multiverse Computing, which is a quantum startup, again, in the same place. So his research interests are in quantum machine learning, quantum computing, optimization problems, and all these kind of problems, let's say. And today's talk, the title is Quantum Machine Learning for Optimization via Variational Algorithms and Coordinate Transformations. So Pablo, I think you can start.
Okay, thanks a lot. Thanks a lot for this presentation. I do not really need to dive in further myself, so let me just make a quick remark, as I was commenting before, that in case you like this beautiful picture, okay, the IPC is over here, super close to the beach. The very same for Multiverse, which is at the mountain, like I would say 4 kilometers away, and we have open positions both at the IPC for postdocs, in case you are interested in quantum machine learning, tensor network, and so on, and Multiverse computing. Okay, so yeah, this talk is aiming to introducing algorithms in quantum machine learning, mainly focusing on our latest work that has to do with variational algorithms and coordinate transformations. Since this is a broad audience, let me first do like I would say, quick summary of where we are right now, right? Like an overview of the current state of quantum computing, how we got here, why we think that it is important, and what we think the future useful steps are in this field, right? So as you may all know,
we have a problem in visualizing the slides. Apparently, they are not fully. I mean, the left part of the slide is out of our screen, so I don't know if it is a.
When you say last part, you mean?
The left part of the slide is out of our screen.
I can't see it properly, so maybe it is
okay.
coming from.
Now it looks okay. I think now it's okay.
Okay, let me try. Yeah, this is fine.
Yes,
you can
yes,
see it?
It's fine.
Okay,
yes.
So,
oh, okay, we have a question.
We have a question, Pablo.
Yeah, it's a question about it. If you go back one slide.
The picture?
No, the title. I wonder because variational algorithms, that's a part of quantum machine learning, you know. So is it like the title quantum machine learning for quantum machine learning? Is that like the tautology?
No, because variational algorithms is just like a subspace of algorithms inside quantum machine learning. So I mean, you can employ other techniques, and this is just focusing on this part of variational algorithms. Is that answering your question?
Well, so you will talk about optimization using quantum machine learning and specifically variational algorithms.
What do you mean that I don't talk about that? Sorry, maybe it's that I don't hear properly because you're at the very back, or?
I see. Yeah, I guess you'll talk about it anyway. Let's just move on.
Okay.
Okay. In case you have any question later on, just let me know, okay? So, yeah, since this is a broad audience, let me just catch up. So you may all know that this whole field was born with Feynman's idea that, okay, if nature is quantum itself at the very, very small components of nature, maybe we need nature physics, nature phenomena in order to describe those behaviors, right? Those patterns. And well, this idea that we should be employing something else other than classical solvers in order to describe nature led to many discoveries and a lot of work on the field, right? So first, during the first decade, we encountered that, okay, we could really develop theoretical stuff, theoretical background for the whole field of quantum computing, in the sense that we were able to prove that quantum phenomena can in fact be useful to perform computations, to do operations that probably classical computers couldn't do ever. Okay, then we went for, I would say, a broader scope, trying to actually build up the hardware to support those algorithms. Okay, the quantum support for the quantum algorithms, launching the very first, I would say, prototype of a quantum computer in 1998, which is mainly based in nuclear magnetic resonance. After that, after seeing that we were able to somehow control nature at our favor, we go through this era of quantum control, in which we basically realize that we can even go further, controlling photons, controlling superconducting circuits in order to build qubits. Okay, after that, and already, let's say, driving through the field of quantum computing, quantum algorithms, and already quantum machine learning, we enter in this era of trying to merge quantum stuff, quantum hardware with classical solvers. Since quantum hardware is still noisy, we are undergoing the era of NISQ devices, in which our quantum hardware is still not robust. We are trying to get the most out of it by mixing it with classical computers, with classical solvers. And since that moment on, we enter in this kind of race, in this road towards quantum advantage, in which we want to, either by means of merging classical solvers in quantum computers, or simply by getting all the capabilities out of quantum hardware when it's ready, get a performance, okay, that might overcome somehow the one given by classical computers. So as I was saying, through this messy roadmap, through this, let's say, schedule of good contributions to the field, quantum machine learning arose, okay? And we will see what this is and why do we care so much about quantum machine learning nowadays, and regarding near-term approaches to take the most out of quantum computing. So as I was saying, right now we are going through this era of noise intermediate scale quantum devices, in which we still do not have a robust system to rely on in order to land our quantum algorithms, right? So this may sound discouraging in the sense that, okay, here we have the words noise, intermediate, which is not so good if we are physicists or mathematicians trying to come up with useful algorithms with useful solutions to solve a problem, a challenge, right? But in practice, this only means that there is like a limited range of applications that one can explore with quantum hardware because of the strong constraints in the number of qubits, the connectivity between qubits, the circuit depth, which is basically the number of operations you can perform with your qubits, and so on, right? In this case, at this very stage, one could either think that, okay, this is still far from reach, far from our scope, we should abandon the idea of coming up with a quantum computer, right, the robust one, or one could simply look at it as a challenge, which is plausible and useful in the future, right? And it is all a matter of focusing on the most promising promising applications of quantum computing. In our case, and also in the case of I would say, most part of the community. One of these applications is quantum machine learning. So for those of you that are not familiar with this term, quantum machine learning is just the intersection between machine learning, classical data analysis, okay, as you all know, and quantum computing. So here one could think of quantum machine learning as the application of machine learning techniques in order to better recognize and better understand quantum data. Okay, but this is not what we mean in here. We mean the other way around, which is take advantage of quantum properties, quantum phenomena, in order to improve our machine learning algorithms. When we say improve, we mean handling larger volumes of data more efficiently, okay, speeding up training times of current techniques, or simply coming up with new algorithms ruled by this new paradigm that can simply not be replicated in terms of classical solvers. And here, as I was anticipating before, one question arises, right? In spite of the physical limitations of NISQ devices, can we indeed start navigating, looking into research lines to overcome classical machine learning algorithms by means of using quantum computers? Since this requires a bit of knowledge about what machine learning actually is, let me just make a quick overview of the type of problems we can run into in machine learning. We have supervised learning algorithms like classification, regression, and supervised learning algorithms like clustering or generative modeling, and this paradigm of reinforcement learning, which is mainly based in decision making. But if one dig a bit into this, one can easily realize that most of these problems can be understood as optimization problems, in which you have a global minimum, okay, of a desired cost function that you are trying to target, so that you find the optimum solution to a given problem, right? This could be the correct labeling of pixels, given probability distribution, some kind of distance between data sets, between entries of a data set, whatever. So here we are looking into this optimization process through the lens of quantum resources as one more tool to come up with useful answers. Particularly, we are employing this paradigm where we merge quantum and classical devices, leading to what is called hybrid quantum algorithms. One important remark in here, let me just remind you that quantum itself has the potential to solve problems on its own, in the sense that you can perfectly build a theoretical quantum algorithm finding the answer for some problem. As you all know, for example, Grover's or Shor's algorithm do that. But at the current state of development of quantum hardware, we need something else. And this is the reason why we are relying on classical devices for constructing hybrid solutions. Moreover, there are some other inconvenience, which is the fact that we're still searching for the right subspace of solutions of problems where quantum could be useful, because nowadays quantum is mainly intended to perform computations that cannot be simulated classically. So that for that end, hybrid approaches are the best way to integrate quantum in the era of NISQ devices, right? And since we are talking about hybrid solutions, let me just introduce the main guy in our equation, the type of algorithm that everybody in the community, well, most of the integrants of the community are using nowadays, which is the variational quantum agent solver, in order to make use of quantum hardware on top of classical devices. As a summary of how this works, well, you basically have a two-step algorithm where you can divide the whole process of the optimization procedure into two cores, okay? A classical one and a quantum one. The objective of an optimization process is basically minimizing, like in a variational procedure in classical terms, a Hamiltonian, so that you can find the ground state of this Hamiltonian. In order to do that, you are proving by trial and error quantum state, okay, that you are getting out of a quantum circuit. So this is where the quantum stuff enters into the equation. You have a quantum circuit where you inject an initial state, perform some computations in the shape of logical gates with some variational parameters, which will be varied by means of a gradient method in the classical side. Okay, from the quantum circuit, you extract a final state, which will be the state that you will inject into your Hamiltonian and see what the energy of that state is, if you are close to ground state or whatever. Okay, the quantum stuff is basically the set of computations you perform on your initial state, okay, so that you can get the final state out of it. The classical solver takes care of evaluating the function, the Hamiltonian, at your given final state and varying the parameters inside your quantum circuit. Okay, this is the reason why it is hybrid and why, basically everyone is using it, because it is super straightforward, okay, the way it works. In case you want to dig a bit into this method, here is a review. And well, now I would like to mention what the cons and the pros of this method are, okay, because this will be important for the work that I am presenting. It is basically the base of it, okay, the reason why we work on a solution or proposal for a solution for the inconvenience of these methods. Okay, so first of all, the pros. Since we are dealing with a quantum system, okay, we are performing logical operations on top of these qubits. We can access a space of solutions which can basically not be simulated classically, okay, because of the number of qubits, because of the huge Hilbert space you are trying to explore. This is out of scope for a classical solver. Even if you could do it with a classical computer, this NISQ approach with the VQE is a natural way just to simply alleviate expensive calculations, okay, conducted by means of these classical resources. Good thing is that this VQE does not really need a huge, I would say, apparatus in order to prove usefulness, to develop some hybrid algorithms. Okay, there are already some useful algorithms around, and this is something you can already do with the noisy machinery we have nowadays. But of course, this all comes at the expense of some cons, right? First of all, there is a complex trade-off between.
Question.
Yeah.
Be loud, please.
Can you go slide back?
Yep.
Yeah, I wonder what's the assumption on the knowledge that you already have before you start doing this. So I assume you know the Hamiltonian, right? Do you also know it's?
Assuming what?
You already know the Hamiltonian, right?
Here?
Yeah, the Hamiltonian is known.
And do you already know the ground state energy?
The ground state energy is unknown.
You are trying to look for the ground state energy. You have this landscape of solutions, okay, in which you are moving around, and you are basically varying the parameters inside your quantum circuit, okay, to move around your landscape of solutions and get a different energy, okay, hopefully less than the previous one in the previous, lower than the previous one in the previous iteration. So the assumption here would come, for example, at the very beginning when encoding your data, you can basically constrain the subspaces of data samples you're introducing in your quantum circuit. For example, that could be a bias thing. But you were meaning at the very end?
Yeah, my question was at the very end. I also wonder, when do you stop the circuit? When do you stop mining?
Commonly, it is done when you find some kind of flat plateau, in the sense that even if you go further with the iterations, you don't really get a decrease in the energy of your system. And this is something that might not be related to the fact that you are at the ground state of your Hamiltonian. And this is one of the problems we were trying to tackle with our proposal. So commonly it is done in terms of number of iterations or in terms of the variation of your energy. because you don't want to spend a lot of time stuck at the very same level, right? So you have to establish some kind of tolerance or cutoff. And that's where you usually stop running your VQE. Is that answering your question?
Yeah, maybe one last one.
Yeah.
If I may. This is very similar in the task to quantum annealing. Are you aware of any connection?
To quantum annealing?
Yeah.
Yeah, but, okay, this is more profound, but quantum annealing is not based on logical gates. There is one paradigm in terms of quantum circuits where you can find something close to quantum annealing, which is the QOAO, which is a different solver other than a variational quantum agent solver, which tries to connect both worlds, quantum adiabatic solutions, which are the ones you are mentioning with quantum annealing, and quantum circuits. In case you want to check it out, I can give some references later about that. But those are two different paradigms. And yeah, it has some complexities, this quantum annealing. For example, the fact that it is super difficult to scale when you want to perform some operations. You need to introduce many qubits working adiabatically and so on. So yeah, in case you want to discuss it further, we can talk about it later.
Okay.
Sounds reasonable?
Yeah, thanks.
Yeah, no problem. So yeah, so I was saying some cons coming, for example, from the fact that it is very difficult to find a good trade-off between the ansat expressibility and the way you convert towards the ground state of your cost function. What does it mean? It means that here we have the advantage using quantum circuits, quantum systems, that you can explore an exponentially huge Hilbert space, right? Something that we cannot do with classical solvers. But this comes at the expense of difficulties in the way you navigate throughout your landscape of solutions. This is something that has been proved recently, okay? And what this group at Los Alamos, okay, New Mexico, showed is that even if it is useful to go for a huge ansat, not to be close to the capabilities of classical solvers, we have to perform some kind of cutoff, okay? It is needed to constrain somehow the space of solutions we are exploring, constraining the entries of our unitaries, okay, the ones we are applying on our quantum circuit, just not to encounter, for example, flat plateaus in our landscape of solutions, okay, in the sense that here you can see that if this is the independent variables, okay, and the y-axis is the dependent one, you see that this is super bad for a variational algorithm in the sense that if we are basing our changes or our modifications of the logical operations on how much our cost function varies, okay, this is super bad because in this zone in here and this zone in here, we will have basically no useful feedback out of the quantum circuit, okay, out of the variations of our wave function. Instead, in here, in the superior one, we see that this is like a convex curve, basically spreading more broadly than the one below. And this is coming from the fact that we are restricting the subspace of solutions we are searching at, okay? This has been proved to be super valuable for hybrid approaches and VQE.
Pablo,
yep.
I mean, a question which is probably unrelated to your talk, but if you know the answer is fine. Otherwise, I sometimes heard the slogan that even non-gradient based methods suffer of the barren plateau, which is surprising because if you have a barren plateau, I mean, if you have a non-gradient algorithm, I would imagine that you move in any case. So even if you are in a flat plateau, you will move out quite easily. Do you know a bit about this issue or not?
No, but in fact, it is one of the things I was going to comment at the very end of my presentation because I'm looking at precisely that right now.
Okay.
That I would like to see what happens when you use other methods apart from gradient descent in order to come up with useful answers for this ground state situation. Yeah, it is a super good question. Yes.
Okay, thanks.
Yeah. So yeah, one more con. as I was anticipating before, it is very difficult to target the right space or subspace of solutions, mainly because the way we usually employ quantum circuits is by it's like a black box. Okay, the same way you deal with neural networks nowadays, in the sense that we do not really have a good control of correlations inside our system. Okay, we are just introducing some kind of answer that we think is good, but we usually do not have a precise analysis of convergence and so on inside our system. So we don't really keep track of correlations. We just say, okay, this will be useful. We will try to vary the parameters inside our quantum gates, and hopefully we'll come up with a useful guess for my ground state, right? But this is not a precise technique. Moreover, there are some other complexities not coming from the algorithm itself, but the quantum hardware. Okay, it has also been shown that noise induces convergence issues, in the sense that if you try to, I'm referring here to current, okay, quantum hardware, noisy quantum hardware. This would not happen for fault-tolerant quantum computers, okay? But for NISQ devices, this is happening. In case you try to introduce a lot of quantum operations inside your quantum circuit, you get, again, to this point of flat plateaus and local minima, okay? Which is something we are trying to avoid in our optimization process. Also, we have a few minor, okay, minor in the sense that are not a milestone as the three I mentioned before, which is the fact that we cannot encode mixed states in our quantum circuit, because that is exponential in the number of qubits. The same for tomography, okay, the same for the ability to read out the mixed state out of my quantum circuit, and the fact that there are certain Hamiltonians, certain cost functions that are more appropriate than others. Okay, it has also been shown that global cost functions are an overhead compared to local cost functions, and this all, as I was mentioning, leads to what is called barren plateaus and local minima. The fact that you have a flat landscape of solutions, super difficult to go through, and local minima, which for the algorithm itself seems to be a global minimum, something you cannot escape from, but it is not the optimal solution for our problem, okay, which is encoded in a different, I would say, place inside our landscape of solutions. Okay, you get stuck at the point that you wouldn't like to be in. So here our paper comes up. Okay, here we are proposing some improvement on these gradient methods in order to alleviate the effects of barren plateaus and local minima in optimization procedures. This is the paper I'll be talking about. As I was saying, barren plateau and local minima are there. This is something we can hardly avoid in our current situation, in our current quantum hardware. So we have to look for alternatives. We have to look for solutions. Yeah.
Yeah, a very simple question. So what is the landscape like? So you have a very flat landscape with a few local minima here and there, typically these problems?
Yeah. You mean the meaning of this?
No, I'm asking, could you go to the next slide, please?
Yeah.
Yeah, so when you're mentioning the barren plateaus and local minimas, I'm just trying to understand how a typical landscape looks like in terms of the, say, the cost function. Is it nearly flat with a few rare local minima?
Yeah, that's usually the case. Yeah, and sometimes the ground state. Yeah.
Right, these local minima are actually very far from being even close to the global one.
Yeah, I was going to say that. Yeah.
Okay.
Yeah, exactly that. Yeah. And building on that, it is not only the fact that they are far, but sometimes they resemble the ground state in the sense that they are close in energy. So yeah, this is a very difficult problem to tackle, and it is usually the case you encounter.
So they are close in energy, but very far in fidelity. So for example, because I guess that if this this local minima is close in fidelity to the ground state, probably the solution will be as good as the true one.
Cannot be if it's close in fidelity, that means you're already close.
Exactly.
So that means you're basically close to the global minima and the little portion.
Exactly. So probably what happened is that you are close in energy, but the fidelity is horribly bad, right?
Yes. Yes.
Okay.
Sorry, let me ask one more question. The reason I'm asking is that basically there are a lot of other problems, not necessarily even quantum problems, where you face a similar issue.
Yeah,
that
yeah,
your
it's the same. Yeah, it's the same.
shape is nearly flat. So
Yeah.
I'm just curious whether the methods you're going to describe, whether they're also applicable in these other cases.
That's the other issue I was going to raise at the very end. It is not only that I'm looking into other type of optimizers other than gradient descent, but other types of problems. I'm also looking into things related to classical machine learning and optimization methods in tensor networks. Yeah. I mean, the questions you are having are precisely the ones I had at the very moment I wrote it up. So, yeah. Should I continue? Do you have any other question?
Seems not. So yeah, please go.
Yeah. So yes, we were saying this barren plateau and local minima are obstacles in machine learning, okay, even in classical machine learning, but it has even a higher impact on quantum machine learning. And we have, as I was mentioning before, several sources for these vanishing gradients, okay, these barren plateaus coming from the algorithm itself, the answer, the expressibility of our system, and the hardware, the fact that we have noisy devices going. So just for you to have the picture in mind, if we have a cost function, we are trying to minimize, we are moving along the direction of the independent variable just to see how the cost function varies so that we can apply some kind of gradient method in case we get stuck at this point P and we compute how the gradient is at the very same point P. Even if we go for high values effects, we will not move at all towards good values effects so that we can go towards the ground state. Okay, and you also take the risk to fall into a local minima where you can really not escape because at the very end this looks flat. Okay, and you should really get a huge how to say impulse in order to get out of the local minima, something which you can barely get in gradient descent methods because of convergence issues. Okay, we can comment on that later too. But this is basically the problem. You try to come up with solutions in order not to get stuck at flat plateaus or local minima. Because if you encounter these issues, there is no further efficient optimization possible, right? And this is a very, very active area of research in the community, not only, as we were saying, in quantum machine learning, but also in classical machine learning, neural networks, and all that kind of stuff that relies on gradient methods and probably other kind of solvers, optimizers. Here you have some references in case you want to dive a bit into these wonders, okay? And our proposal here relies on the following. It might sound like a very basic approach or simple in terms of understanding how it is going, but it seems to be leading to good results. So I think it's a promising approach. The thing is that we are getting stuck at dimensions that are orthogonal to the cost, right? The cost function is always an orthogonal dimension to our independent variables. So maybe we should find the way to move throughout this dimension, which is the cost function, as one more coordinate to perform optimization over. The way we are doing it, the way we are trying to incorporate this cost function as one more variable to vary and get the convergence, the optimal convergence in our optimization procedure is by means of two different ways. First of all, we are...
Yeah. I mean, to understand, so essentially, this approach that you are proposing bring a change of ansatz, right? I mean, because okay, I will see probably better later, but it looked that to go to a direction which is orthogonal to the directions that you have in your ansatz, it means that you change the ansatz. So the U, let's say the structure of the unitary get changed in order to explore an orthogonal direction. Am I right?
No, because this is coming from the classical side. It is the way the solver, the classical solver, interprets the cost function.
Okay, let's see.
The way it represents that dimension. Yes, so we are doing this. We will be explaining it a bit later. So yeah.
Next question by Alexei.
Related, actually, maybe can you illustrate like naively this idea of this extra variable, maybe based on the
plot
that you have on the slides, with which illustrates the plant. Yeah.
I have more pictures coming on, describing the process for each one of these approaches. Yeah, so you will see the picture and so on. Yeah. Okay. Yeah. So yeah, two different methods. First, I'm using a change of the coordinate system. Instead of using a Cartesian one, we are moving back and forth from the Cartesian to hyperspherical coordinate system. And the second one, we are straightly using a variational frame, okay, a rotational frame, in order to move throughout directions that are not orthogonal to the original independent variables. And I will be explaining these two methods more in depth right now. First of all, the hyperspherical coordinates. As I was saying, this method relies on describing the position of our point in our landscape of solutions instead of using Cartesian coordinates, using hyperspherical coordinates. The reason why is that if we have this picture in mind, okay, imagine that we have here just one independent variable so that you can match the drawing with the equations. So for you to see it clearly, we have this flat plateau, we have a local minima, and here the ground state, for example. The fact that you cannot get useful updates on your independent variable as you move throughout the landscape of solutions is basically because you get stuck at a dimension which is perpendicular to the cost function, so that when you try to compute the gradient of your cost function, it is almost zero. What we are proposing here is the first step describing this point P, instead of using Cartesian coordinates, using hyperspherical coordinates. The reason why is that if your solver, your classical solver, understands the coordinates as hyperspherical coordinates, you can use that way of describing your point to update the new variables inside your hyperspherical description and come back to the Cartesian one when you want to basically know the value of your cost function, which will be the one.
Here you are already adding a coordinate, right? You are adding the radius.
Yes, but you can yes, but since we included the cost function as one more variable inside our system, it is the same number of variables.
Okay.
In the sense that, yeah, it is n+1, where that one is the cost function or the radius in the case of a hyperspherical coordinate system. Okay. So the idea is that in the gradient descent method, we perform the update of parameters on the new set of coordinates on theta and r, because on that set of coordinates, the cost function is no longer perpendicular to the variables, so that we can freely move throughout these variables. Okay, with that, we will get an updated point P prime, which is in here, that we can right now describe in terms of the original variables in which we want to write our cost function to calculate the gradient of our cost function, because that reference has to be on the original reference frame, on the original description, because that is the one where you know where the ground state is. Not the new one, but the previous one. Okay, the changes are produced on the new set, which is no longer perpendicular to the cost function, but the reference of your energy has to be given in the original description. That's the one you know. Okay, this is like an artifact, and it's artificial, of course. Okay, so you want to have this reference of the cost function on the original reference frame. So once you change your coordinates on the new set, you calculate your cost function on the original variables. Okay, since we are dealing with a gradient descent method, we will then compare that updated version of your cost function with the previous one in order to perform new changes on the new set of variables on theta and r. Okay, which you remember that are those not perpendicular to the cost function, so that you can really move toward these directions.
I have a couple of questions. The first one is, what's the advantage of this mapping with respect to changing the cost function directly?
Changing the cost function to represent it in a basis where you can describe it.
Let's say, since you say I have a cost function which is because
once you change the cost function, you still get the fact that maybe you are moving throughout r and theta, but if you don't change again, it is still the same problem at the different representation.
Okay, and the other question is, do you perform this only when you got stuck, or you perform at the very beginning?
That's a very good question. You can basically take two approaches. Either you do it back and forth all the time, or when you get a vanishing gradient, you produce this approach.
Correct. And which one of the two you do? The second one?
No, the first one. I just wanted to see how this performs when you go for this from the very beginning. But that's also something we studied. Yeah, it's also in the paper in case you want to check it out.
Okay.
And yes, as this procedure goes on, you just go back and forth so that you move throughout the hyperspherical coordinates, but compare the energy using the original description. And that would be the hyperspherical approach, okay, a simple version of how it performs. And here I have some benchmarks based on actual papers well known in the community of quantum machine learning. For example, here I have the one I was mentioning about the global cost functions against local cost functions. Here, the researchers at Los Alamos prove that when you have a cost function written with global variables, you get an exponential vanishing gradient, something that you don't get when using local variables, where you get a polynomially vanishing gradient. When you compare their approaches, you see that they are trying to see how an optimization procedure is done, is performing on top of a quantum circuit. When they use a global cost function for 50 different ansatz inside our quantum circuit, they get a success of 30% using more than 100 iterations. But when you use local cost functions, you get a success finding the ground state of your system of 98% with just 30 iterations. But with our hyperspherical coordinates, we saw that, I mean, amazingly, you can get a 90%, a 98% success, or even 100% success for the very same 50 ansatz with just 5 iterations. This is probably proving the fact that you not only need to look at the cost function itself, but the way you move throughout the landscape of solutions, because you are probably using a reference system that is not so appropriate for that cost function, in the sense that you can use a hyperspherical description, which will probably land better results. This is just one example. Then you have this other paper introducing what is called a quantum singular value transformation in order to generate arbitrary function transformations using Taylor approximations. It is an extension of quantum signal processing. Again, what you have to keep in mind is that this is an optimization procedure in which you try to find good variational parameters to find the ground state of a system. This is just some information for you to dive in those papers in case you are interested. So for getting
question.
So I wonder, these like hyperspherical coordinates, it's because it rescales somehow what's important in your model, depending on the parameterization. So the fact that you got a convergence in just 5 iterations, that's probably highly dependent on the fact that you use hyperspherical coordinates. But if you use some other, or if you use some other model, the performance could be different, or maybe better, maybe worse, right?
When you say
It's like-
model, you mean Hamiltonian? When you say model, what do you mean by model? The model of the quantum circuit, the model of the classical function you are trying to solve?
Yeah, like a cost function.
Yeah,
If
it could be.
actually-
Yeah,
It's just suddenly by hyperspherical coordinates, you suddenly rescale the, let's say, spatial step. Something that used to be like a dx. Now,
Yes.
if you like d theta, then d theta in the like the right hand side results in much bigger dx than on the like middle, right? Because it's kind of scaled. It's a projection.
yeah, but that's coming precisely from the fact that you are moving throughout. Yeah.
You are jumping just much faster in certain directions.
Yeah.
Because the coordinates you chose.
Yeah. That's the thing. Yeah.
So
Because probably. Yeah.
Let's say the optimum is somewhere on the left, and all the way on the right there is barren plateau. Then this would probably hurt you actually.
Because the gradient in that case will move to the left.
Yeah.
I mean, the gradient is already, I guess, in the right direction, but is moving very slowly. So this keep moving in the right direction, but much faster.
Yeah.
Yeah, because you can basically, if you think in terms of the reference frame, not the description of the point, okay, as we will see later, if you somehow turn your reference frame, you are still moving on that direction, but with a different inclination somehow, because you're moving throughout the radius or whatever. So still the direction is the direction at which you are pointing is almost the same, in the sense that it is just surroundings of it, but the inclination is much more. It's steeper.
Somehow, I guess that let's say the magic of all this fact is probably related to the fact that let's say the gradient is always pointing towards the best direction. This is by definition of what the gradient is.
Yes.
Now, you are essentially saying that since initially you have an n-dimensional gradient, then become an n+1 dimensional gradient. So the two best directions will be, let's say, similar because they differ just by one coordinate.
No, but so, it is not only, sorry, it is not only a matter of introducing one more coordinate. I tried to introduce one more coordinate, which was not the cost, in the sense that you simply over-parameterize your system, introducing one more variable, and it doesn't work. You have to construct a self-consistent method in which the cost function enters the variables you are varying, because that's the direction you are interested in.
Yeah, because
so
it's the magic. I understand.
Yeah.
Okay.
Yeah, it is a self-consistent process, and the cost has to be in, because I thought at the very beginning, okay, but maybe this is coming just from the fact that I'm extending somehow the basis in which I'm working on. So I am over-parameterizing my system as in neural networks, and that's the reason why it is working. But
we already know that if you over-parameterize will work, but you have to over-parameterize by a lot.
Yeah, I was going to say that. Yeah, a lot, not just one variable.
Exactly. Here, instead, just one variable is enough because it's an optimized variable, let's say.
Yeah. Because it is the one moving throughout the direction you are interested in. It is not just extending the landscape of independent variables like till infinite, but moving throughout the one you're interested in, the orthogonal one.
Okay, thanks.
Okay,
there is another question.
So couldn't you achieve the same like speed up in learning rate simply by, not doing this fancy stuff with hypercoordinates, but just simply increasing the step by which you randomly jump to a different?
You mean like in the gradient distance, increasing delta x?
Yeah, exactly.
No, that usually doesn't work like that. No, it has to be a trade-off. Because still, if you increase a lot delta x, if you have a zero gradient, it is still zero. You get nothing out of it.
Oh, I see.
Because when we mean flat, we mean flat. We mean zero variance. like exponentially flat. And maybe if you overcome that issue, because you, I don't know, you increase delta X by a huge factor, you are basically moving randomly around your landscape of solutions, because you are basically jumping from one side to the other with no continuous sense, right?
But isn't that what's happening when you have these hypercoordinates?
Because these hypercoordinates, I think the issue, as Pablo was saying, I think the magic is really that this new coordinate is really the cost function. So it's really making you move in a special direction, which is the direction that you want to optimize.
Yes, because at the very end, the result of your variation algorithm is basically, it can be reduced to moving throughout the direction of the cost. That's the thing you are interested in when you go for a variational algorithm. You're basically trying to minimize a cost function, which is nothing but moving throughout the direction of your cost. If you find a way to artificially move throughout that direction, in the sense that the machine, the classical solver, understands your variables as something moving throughout that direction, you are performing a shortcut, because you are already moving throughout that direction when doing the optimization procedure. You see, and that has to be the cost, because that is the one you're interested in.
Okay, thanks.
Yeah. So here, I think I have a bunch more of examples, but since I'm running a bit out of time, let me just prompt it out, and you can check the references. It is basically some other achievements with this hyperspherical description. And the other method is the variational reference frame, which might be more intuitive for you guys. So it is also for me. So in this case, we are not changing the way in which we describe our point, but the reference system in which the point is described. Okay, it might sound the same, but done in a different way, but the correspondence is not one-to-one. Okay, you have to be careful because of some details. Okay, at the very how to say basics of this procedure. So here, the goal is the same, moving throughout a direction which is orthogonal to the independent variables we start with. That is the direction of the cost. In order to do that, we are going to rotate our reference frame so that I have some equations in here, so that when performing the update of the variables, we do that update on the new set that we have obtained after performing some rotation in our landscape of solutions. For example, if we focused on a particular independent variable and the cost function, the independent variable x, let's suppose it is xi, this one in here, the one we are getting stuck at. We are interested in moving throughout this direction, but we encounter a flat plateau in the landscape of solutions. We are not able to perform gradient distance based on the change of my cost function. So I simply rotate my reference frame with a rotation that can be, I don't know, can belong to SO2, or maybe I can rotate more than just one independent variable in order to perform such an operation, whatever. Okay, I tried with a few things, but the idea is the following. I rotate my reference frame, and I now move throughout what I call x-rotated, XR. If I move throughout XR, I get a cost FR, and now I can move throughout this direction here and this direction here, because remember that my cost function in the rotated reference frame is centered in one more variable. So I upgrade these variables, independent variables, and the F rotated in order to get an updated version of my cost function in the original reference frame, as we were mentioning before with the hyperspherical description, but in this case, not changing the description of my point, but the reference frame in which I describe my point, and just go back and forth doing this very same idea, right? We perform the upgrades of my variables on the new reference frame and compare the new cost function generated by this upgrade of variables on the new reference frame with the original cost function written on the original reference frame. This is the very same as the hyperspherical description in terms of this self-consistent method where the cost function enters as one more variable, but the way it is done is different, okay? Because we have this rotation of either planes, or it could be hyperplanes, whatever works, because you can not only rotate one variable at once, but a few of them. And you can also perform optimization over the angle you are rotating the reference frame over, which is something that we also did. Okay, there are many more details coming on, or at least at the guts of the algorithm, but I think I won't have time to present them now. So in case you're interested, we can go through it afterwards. And again, some benchmarks. Let me remark that even if using the hyperspherical description, we got, how to say, more remarkable results in the sense of improving a lot the current state of solutions for those certain sets of problems. Here, the variational algorithm, the rotational reference frame, whatever you want to name it, seems to be more robust in the sense that maybe it doesn't achieve an amazing solution compared to the previous one, but it improves, at least until the point we have seen, a broader set of problems. Okay, it is more useful because it targets a broader set of algorithms, of optimization procedures, of problems, whatever you want to call it, but the results are not so remarkable in the sense that the gap with respect to the previous solution is not that huge. And again, here you have some examples. This variational quantum linear solver in which you perform a hybrid algorithm in order to solve a linear system of equations. Here you have the original, the red one, solution for your optimization procedure, and then the green and blue ones for the ones obtained by means of this rotational reference frame. Again, for this paper in here, since I'm running out of time, let me just go a bit fast. Here
no,
again.
no, you don't need to go fast, Pablo.
Okay.
You can take your time because
okay,
we have.
Okay, I was running a bit because of that, but okay, I appreciate that.
Time. Please take your time.
Okay, thanks a lot, because I was kind of rushing through it. Yeah, okay.
Yes,
Thanks. So these are 3 more papers. In this first one, at the very top of the screen, the researchers try to understand what is the relationship between the expressibility of our quantum circuit and the information we can get out of the data set we are trying to classify, understand, in the end, handle, right? In here, we are performing again an optimization process in which we vary some coefficients and frequencies of a Fourier series describing our data, the one we encode in our quantum circuit. And we see that on that optimization process, we have again some gain in the convergence of our variational method. Using this rotational reference frame, we can achieve a lower cost for basically every single optimization step of our iterative procedure. Same for some other methods. For example, this one in here, in which they tackle the issue of the global cost functions against the local cost functions, introducing how to say, a perturbative, yeah, it is in here, a perturbative gadget mapping the global cost function to auxiliary local cost functions, comprehending just 3 body systems, you see that again, if you want to reach the ground state of that global cost function by means of the auxiliary local cost functions, you would employ 140 iterations in this case against the 110 iterations we employ with our rotational frame, optimizing over theta and the amount of independent variables you introduce in your rotational matrices for the optimization process and so on. Let me also remark that I didn't say that previously, that the numbers we are comparing against, okay, this 140, this red line in here, this red line in here, also the ones I prompted before, are optimized versions of the original code. This means that we didn't just take the basics of the code, I mean, the way it is given, just launch it, and we get some results, and we compare that against our most accurate version or optimal version, or the optimal version of our code. We perform an exhaustive hyper-tuning of the parameters of the original code. So when we show these results, we are really comparing best versus best, their best and our best. That's important because you usually try to hide the way it is performed and the how to say, the hyperparameters you are using and so on. We are just basically trying to get the most out of the original one so that the comparison is fair. Just for you to have that information in mind. This is just to say that we perform various more calculations, various more comparisons that are on the paper I showed before. We're still working on that, and more. There are more coming. So, as you asked before, we are still working on this method. We want to explore certain directions. First of all, we want to better characterize the convergence of our analysis, how it works mathematically. Why does it work better than simply over-parameterizing your system? We want to generalize this to machine learning algorithms, not only coming from quantum machine learning, but in more general terms. And we want to see what happens when we employ other optimization methods, like, I don't know, for example, Nelder or whatever, other than gradient distance. And since this is a talk about quantum machine learning, let me just talk about a few useful current trends in quantum machine learning, at least something that I like. Here I present to you first all the stuff, the quantum machine learning stuff related to quantum data. You know that algorithms can be classical and classical in the sense that you use classical data and a classical solver. You can use classical data and quantum solver, quantum data and classical solver, and quantum data and quantum solver. And this latest I mentioned is the one which is right now closer to give some quantum advantage. As you know, Google claimed, I would say 1 year ago, that they had achieved something out of scope for a classical solver. And this is coming from the fact that they are trying to analyze quantum data with a quantum algorithm, which is probably the good correspondence in order to get the most out of our quantum circuits. And then a second trend of research called geometric quantum machine learning, which is related to the fact that, okay, we are using quantum circuits as black box. We are not really understanding the relationship of between the quantum circuit and the data we are injecting in our quantum circuit. We are navigating landscapes of solutions full of barren plateaus, local minima, and so on. It's clear that we need to come up with useful and interesting solutions for those problems. And what we are or what the community is looking into in this sense is bringing some ideas from the classical side, something called geometric deep learning, developed, I would say, 6 or 7 years ago by a guy named Michael Bronstein at Oxford right now, where they simply try to create data-aware algorithms, in the sense that if you have a neural network, if you have whatever classical machine learning technique to develop a solution for a problem, you want to introduce as much information from your data set as possible in order to constrain the subspace of solutions you are looking into. This means introducing symmetries that you can encounter in your data set, inductive biases, and so on. Okay, and this is something we are also exploring, and it is done in the quantum machine learning community, mainly from this group at Los Alamos, Marco Cerezo and his group. As I was saying, this is basically introducing tools from algebra, geometry, and topology to better understand the expressibility of our quantum circuits, to better understand how to encode information in our quantum circuits, and so on. And this is basically a link between quantum algorithms and representation theory in order to comprehend how to act on qubits, how to navigate super bumpy landscapes of solutions or flat landscapes of solutions more efficiently, right? And I would say that this has been all, and I'm open to any further question or any further discussion, something you want to talk about. So thank you very much for your attention.
Thank you, Pablo, for your excellent presentation. We have time for further questions. So, perhaps you were showing two approaches, right, to the problems. Did you also try to compare both approaches on the same problems, or because it's that you were showing different problems with different approaches? And somehow I had the impression that the first one, the hyperspherical coordinates kind of seemed to perform better. Can you maybe comment a bit?
Yeah, what we saw is that probably the cases in which it works better are those with specific landscape. So I'm not sure if there is like a magic correspondence between a given hyperspherical description and a given problem, or it's simply the fact that for those specific Hamiltonians, as you were commenting before, it performs really well because for some reason you are able to navigate to go throughout your landscape of solutions more efficiently. But it is not so consistent in the sense that whenever you alter a bit your hyper parameters, for example, learning rate or basically here learning rate, also it could be the encoding of your information inside your quantum circuit, your ansat, the logical gates you apply to your data set, okay? It stops working that well, in the sense that these cases I show here are not so robust as the rotational frame. So when I tried to employ this method with the samples taken from the other approach, it didn't work that well, in the sense that maybe you were able to reach a better solution for some cases, but it was somehow random, in the sense that I didn't have much control over it. You know, I didn't see the smoothness of the convergence.
So basically, to sum up, this hyperspherical approach works much better, but in just certain pieces.
The subspace of solutions is super small, I would say, compared to the other approach, which seems to generalize a lot better. Because for the other approach, by the way, for these examples, we are taking the code. I have to give credit to it. taking the code from Pennylay's website, okay, from Xanadu's company. And there you find a lot of tutorials and so on to learn about quantum machine learning, about quantum computing. So I'm taking the examples from there, which are themselves taken from journals, from articles, from the community. For the rotational frame, I tried 18 different problems, and I found better solutions for 16 of them, in the sense that I compared best to best. Best of their proposal and best of mine. For the hyperspherical description, I think I just got like seven better results out of 18. It is not so robust. Yeah. And this is something I want to understand in terms of equations. That is the reason why I want to dig a bit into the convergence issues, the analytical stuff behind these solutions.
Because so far you don't have an a priori clue when the hyperspherical coordinates will be good or not. You just try and hope.
Yeah, trial and error.
Yeah.
And I'm not comfortable enough with that, so I want to dig a bit deeper.
What about you said that you try. What about applying these methods only when you get stuck? At the end, I didn't get if it is a better idea to go with the standard method, and when you get stuck, you start to use this, or is better. I didn't understand.
I found similar results. At least for the examples I tried. Yes.
So essentially, you're saying when the landscape is not flat, this change will not change much.
Yeah, not much. Maybe it alters a bit the convergence, but I mean, if you are capable of moving throughout this direction, for example, the fact that you are like this or like this does not do too much, right? But if you are like this and you move and you do something like this, then you have the advantage. I mean, the important advantage.
Okay.
Yeah, that's it.
Okay.
Alexei.
Yeah, and so the first approach with the hyperspherical coordinates, does it generalize to basically arbitrary problems, or there's some constraints which problems you can apply it to?
What do you mean by arbitrary? Yeah, I mean, I tried with different optimization problems, both supervised and supervised, different cost functions and so on, if you mean that.
No, I'm basically just thinking if you have literally an arbitrary optimization problem where you have a cost function that you need to minimize, and the set of constraints that you have to satisfy, and you still can you adapt this method?
Yeah, I don't see why not, because the solution is hidden in the way you perform the optimization, in the sense that if you can apply a gradient method on top of it, you can use this approach, because it is taking part in the gradient distance method.
Okay, thanks.
Yeah.
Maybe another question, more technical. So what is the typical number of parameters that you are optimizing in your learning?
Variational parameters, right? The dimension of that set. I would say 100.
100.
Yeah, it is commonly I would say the top bound because of the depth of your quantum circuit. Here I'm only dealing with quantum algorithms or hybrid algorithms, and we are restricted by the dimension of our quantum circuit, how many logical gates you can introduce. So if you count for a general unitary, three, for example, three, because of the Euler angles, 3 variational parameters, that's one logical gate. You might have, I would say, 20 qubits. That's already 60 unitaries, and you have to multiply by the number of layers you are introducing in your quantum circuit. So it is of the order of 60 times number of layers, 200, 300 for the time being. Yeah, but it can be extended. Since for example, for the rotational reference frame, since you can use unitaries belonging to SO2, computationally, in order to do the inverse and so on, computationally, it is not that expensive. You don't really have to construct the metrics of the single, or I would say, how to say, this scramble landscape of rotations where you rotate every single independent variable with respect to the cost. Here you can basically perform something like a diagonal ones and just a plain rotation of the cost function plus one independent variable. And that's very cheap in terms of classical computations.
Sorry, the states that you are, I mean, in all these examples, the states that you are targeting are, let's say, low entanglement, right? Area low.
Yes, but I don't think that's a constraint.
No, but I think constraint for the kind of circuit you are trying, I guess.
Yeah, because of the expressibility. Yeah, I mean, for the time being, probably you can basically simulate everything with tensor networks, because of this low entanglement thing. But the approach is intended to generalize that, in the sense that it acts on an arbitrary number of qubits with arbitrary connections. So yeah,
I'm wondering if, because here it's true that you add a special coordinate, which is the cost function, but I'm wondering if, suppose that the number of coordinates explode. So adding a single coordinate on, let's say, an exponential number of other coordinates might, I don't know, reduce or modify the effect of this. I'm wondering if that will play a role. I mean, suppose that you have a deep, really a deep circuit, because, I'm thinking about the problem that I faced with deep circuits.
Let me.
So
Yeah, keep going, please.
I mean, I'm wondering if the methods that you presented can be useful when you deal with deep quantum series.
Probably just because there's this work also coming from Los Alamos. I mean, these guys are top, where they first showed that whenever you have this over parameterization of your system, in the sense that you introduce a lot more variables than needed, compared to what you expected at the very beginning. When you do that, it is true that you erase local minima and flat plateaus, increasing the number of operations in your system. But I think that there's a point that you where you reach
that is what we also showed in our numerical paper, if you remember. I mean, we showed that when you go to the over parameterized regime, you have the barren plateau, but nevertheless you optimize very well. That was the numerical. I mean, actually, we got in touch because of that.
Yeah, but I don't know if you read it. There is one last paper from that group. I think it is 3 weeks ago, saying that. Yeah, so from that limit on, there's no really an advantage. I mean, you come again to the point of having exponentially flat plateaus. That is what I was intending to say.
Okay. So over parameterize is good, but too over parameterize is bad again. Eh?
Yeah, I think it is something like that, because it converges to some Gaussian processes. They prove that, and the gradient becomes exponentially flat, even for over parameterized systems.
But even in our case, it was exponentially flat, but nevertheless, you were reaching, let's say, a local minimum that was essentially as good as the global one. But now you're.
That's probably depending on the cost function, right? If you are reaching the local minima, which is close to the ground state, that is something that depends on your cost function. It is not the ability to navigate the landscape of solutions, right?
No, you were not trying. That was exactly the point, that you don't navigate much, but nevertheless, arbitrarily close to your initial point, there was a point that was performing quite well.
Yeah,
that on our result, and was, let's say, confirmed by Marco Cerezo and Marco Cerezo and so on.
Yeah.
Now you say there is, okay, I will check for the new, yeah, maybe we can
I
check.
don't want to make a mistake, but there is something like that they even over parameters in the system, they get these exponentially flat gradients, so that they cannot really go farther in the optimization process.
Okay, I will check. Thanks. Yeah.
Probably if you are in the surroundings of a local minima that is good enough for your solutions, for your expectations or goals, that works out. I mean, that's good enough for you. But in terms of the ability to modify your cost function along the whole Hilbert space and so on, yeah, I have my doubts in there.
Okay, yeah, maybe we can chat better. I mean, later. Yeah, thanks.
Do we have any other questions? Seems not. So then let us thank Pablo again.
Thank you, guys.
Okay. Thank you very much.
Yeah, thank you for having